Hello friends, welcome to TechCube Gate classes, an initiative by TechCube faculties. My name is Professor Vivek Singh Rathore and I am Assistant Professor in Electronics and Telecommunication Department in Government Engineering College, Bilaspur, Chhattisgarh. This initiative was taken by all TechCube faculties across India for empowerment of engineering graduate students. In this video lecture, I am dealing with signals and systems subject, and I have taken already 4 lectures, and this is my 5th lecture. Today, I will be dealing with classifications of signal. So let's get started with our first classification. That is, I think we'll take this as classification of signals. So first classification when we will take real-time valued signal and complex valued signal. So this is real valued signals and complex valued signals. Okay. So what are real valued and complex valued signals? See, when a signal is there, let ft a signal is there, let's suppose it is around 5t. Okay, so 5t is there signal. Actually this is a real valued signal. Okay, and one more example I will take. ft is there, ft is almost 5t plus, let's suppose, j3t. Okay, this signal is complex valued signal. So you can understand whichever signal is having complex part, that is complex valued signal. Okay, so actually real is what? Real is something which is physically existing. This is physically existing, and complex is not physically existent, but it is existing in mathematics. So actually by using imaginary part, many we can reach outcome in fast and efficient manner. So that is why actually real valued and complex valued different signals are there. The best example for complex valued signal, if you take, we see e to the power jt, that is called as Euler's signal. Okay, this is called as Euler's signal, and e to the power jt, if you know, you can write it down in trigonometric form also, that is cos of t plus j of sin t. So e to the power jt is this, and this is there is a complex part, so it is a complex valued signal. Okay, so actually the amount of analysis required for reaching outcome is actually greatly signified, or it is very less number of analysis is required for complex valued signal when we put j part in that. Okay, imaginary part, that is and most common imaginary signal is Euler signal. Okay, so this was first classification. Now the main classification which we have to see in detail is our second part, that is called as continuous time signal and discrete time signal. So let us write it down: continuous time signal and discrete time signal. Okay, so continuous time signal and discrete time signal. See, a signal is there. Okay, let's suppose a signal is there. This is time domain and this is your amplitude. So if a signal is there, let's suppose some any signal is there, and okay, whether it is this or ramp or unit step, anything is there. But when you see, this signal has some amplitude, but it is defined. Okay, the word, it is defined for every time interval, for every time. Okay, means if you see 0.1 second also, it is some value is there. 0.01 second also some value is there. So this signal, whenever a signal is defined for every time interval, every time instant, okay, so that signal will be called as continuous time signal. Continuous time signal. And let's suppose a signal, if we take, okay, when we take a signal, let's suppose and a signal is there which is defined at, let's suppose, at t is equal to 1 second. It is defined at t is equal to 2 second. It is defined at t is equal to 3 second, but it is not defined at t is equal to 0.5 second. So like this, whichever signal is there which is defined for only integers value particular instant, that is called as discrete time signal. So I think you must have understood what is real time signal, what is continuous time signal, and what is our discrete time signal. Okay, so whenever we need to calculate or we need to plot discrete time signal, we have to do a technique. We have to perform a technique that is called uniform sampling from a continuous time signal. Then we can get a discrete time signal. Let's suppose key this signal is there, and let's suppose this signal is there. Okay, this is a continuous time signal which is defined for each and every time instant, and now we need to see its discrete time signal. We need to calculate. So what we need to do is we need to for a uniform sampling. So let's suppose sample values are taken from, let's suppose at this value sample is taken, at this value sample is taken, this value sample is taken, this value sample is taken. So the value may be like this at this instant, this instant, this instant, this instant, and so on. If you can plot, then definitely it can be plotted like this. Okay, like this, but not accurate. For that we need sampling theorem, that is Nyquist sampling theorem, and then we can plot it easily. So what I need, I was telling you that for a discrete time signal we need to perform uniform sampling from continuous time signal. Okay, so how do we represent these discrete time signal? Because continuous time signal, I think we have already seen, and various operations also we have seen in continuous time signal. So let's see some of the operations and how we can write it mathematically, discrete time signal. So first we will see one signal. Let's suppose time domain is there, and this is actually discrete time signal is defined for only integer value. So we can write here at as n. Okay, n is number of n is the integer value. So, and this is value 0, and actually this axis is called as amplitude, in which amplitude will be there, and this axis will be n, integer value. So let's suppose a question is there and it is given that some value is defined at t is equal to n is equal to -4. Okay, and this value is 3. Okay, let's suppose 3 values there. One value is there, this is at n is equal to 2, and the value is, I think, -2 value, and some value is defined at n is equal to 3 also, and it is maybe it is 2 value. So let's see how we can write it down. So it is written as fn. Okay, earlier continuous time signal was written as ft. It will be written as fn, and it will be written as in curly bracket like this. See, first we need to see at n is equal to -4, value will be 3, so we can write it down as 3. Okay, next see, this value is at n is equal to -4, but for n is equal to -3, some value should be there, so we can write it down as 0. Okay, for -2 also 0 value is there, for -1 also 0 value is there, for 0 also 0 value is there, for 1 also 0 value is there, for 2 some value is there, that is -2, and for 3 some value is there, that is +2, and this you can close it down. So, and here we'll take main arrow, I think I will take it as from red color, where is this is -4, -3, -2, -1, 0. So we'll put a arrow in the n is equal to 0. This is the format for writing it. We can also, I think, we can also write it down as like this: fn is equal to -4 for n is equal to I think, sorry, -4 no, fn is equal to 3 for n is equal to -4, n is equal to I think n is equal to -2 for n is equal to 2, and n is equal to 2 for n is equal to 3, and for 0 otherwise. Like this also you can write it down, no problem for this. So now you understood that how to write a discrete time signal in mathematical expression. Now if we have to perform some operations like time shifting operation, so what we can do it, see, two shiftings are there, either we will do delay or advance. So if I'll tell you both fn minus 2 and fn plus 2 both, so see, signal was there, I think we'll take it as 3 0 0 0, okay, I think 3 0 0 0 and 0 0 minus 2 2 and 0 minus 2 2. This was the value which we this was the expression which we have taken from the signal, and minus 4 minus 3 minus 2 minus 1 0 here 1 and 2. I think this was the case 3 4, okay, 3 4, and for that I think one more 0 was there, we'll do it, okay. So this was the expression. Now if we have to calculate fn minus 2, you know fn minus 2 means what, will shift towards right hand side, okay. So right hand side, the whole value, this all whole value will shift toward right hand side, but the arrow will remain constant, arrow will remain constant, and you need to shift this, how much you have to shift, n minus 2 is equal to 0 if you equate, so n is equal to 2, means 2 plus 2 times we have to shift it. So let's see, every value, like this value was at n is equal to minus 4, and this value was n is equal to I think 0 1 2 2, so you need to add every in every n you need to add plus 2 plus 2, so overall the signal will be, uh, 3 only, I think minus 4 plus 2 it will be minus 2, so we'll take it as n is equal to minus 2, the values are there, and then 0 0 0 0 0 minus 2 and 2 will be there, and this will be I think in here. So okay, what happens, actually the arrow will remain the same, but the values are shifted, actually the values are shifted, so the arrow will point now towards this, because all have been shifted here, so this value will come here, all values are there, so n is equal to 0 point will be at this point. So now you can understand that whenever we are shifting towards right hand side, we are keeping the arrow same and all values are right hand side, or alternate you can think of that, if we are shifting right hand side, then you can shift arrow to the left hand side, then your wish, what you want to do. And for fn plus 2 also it's the same thing, you need to shift left hand side, so left hand side, and arrow will be shifted towards right hand side, so now arrow will be for fn plus 2, now arrow will be around I think earlier it was here, now it will come minus 2, so it will point towards this, and now for fn plus 2 arrow will be this one. So time shifting property, basically in time domain you have understood that, and in discrete time signal also you can, it is very easy actually. Now if we perform some other operation like time scaling operation in discrete time signal, what happens, let's see. So we'll do time scaling property, okay, time scaling property in discrete time signal. So earlier it was fn, okay, now we need to perform time scaling property. Let's suppose we need to perform f2n, okay, so it is a time scaling property, fan something will be there. So let suppose your signal will be fn is equal to let's suppose 3 minus 1 2 and 2, and I think 1, this value is there, and arrow will be at this point, okay. Now what you need to do, you need to do f2n for this signal. How will you do that? Earlier I have told you that whenever a signal is there, and the time axis is there in x-axis, So the values, whatever values will be there, it is just divided by the scaling factor. So let's suppose this is actually n is equal to 0 value is there. So n, for n is equal to 0, what value is there? We'll plot it from here. So n is equal to 0, the values are 2. For n is equal to minus 1, the value is minus 1, so I will take it as minus 1. And for n is equal to minus 2, the value is 3, so I will write it as 3. And here it is I think 2 only for 1, so we'll write it as 2. And for n is equal to 1 2, and here it is 1. So this can be plotted as like this. Now what you need to do, we need to do f of 2n, means we need to scale with 2. So I have told you whatever the values will be there, you just need to divide it. So earlier actually the values were this is minus n is equal to 0, this is minus 1, this is minus 2, this is 1, this is 2. So now what we have to do, we have to divide with the scaling factor. So we need to divide with scaling factor all n values. So we'll get it as minus 2 by 2 is minus 1, this is minus 1 by 2, this is 0 by 2 is 0, this is 1 by 2, and this is 1. See, I have told you earlier also, just in this lecture only, that discrete time signal is defined only for integer value. So this is not an integer value, we have to calculate, discard it. Minus half, we need to discard it. So now f of 2n, if you want to plot, you can see the values. Only this value at minus 1 will exist, because now the values are minus 1. This value won't exist, 0 value will exist. Okay, so it will be at this value, and this value 2 value will exist. So this value will be 2 by 2, 1 value will be exist. So integer, these values are not existing. Okay, so as you can see, see, we have earlier seen that whenever we scale with a is greater than 1, we always get a compressed signal. So here also you can see, earlier it was starting from minus 2 to 2, but now the values are minus 1 to 1. So the signal has been compressed. But you can also note it down, or you can also see that the some of the values, I think some of the values are neglected, or they have been ignored in the f2n. Okay, so from this you can get a conclusion that whenever we do compression, okay, some values are neglected. Okay, some values are not taken. So some values are not taken, and this process will lead to loss of samples. Whenever we do f2n a is greater than 1, we will get loss of sample, and this process is called as decimation. Okay, decimation. Now whenever we want to do scaling factor with a is less than 1, let's suppose we need to do f of half n. So let's try with this signal only. This signal was 3 minus 1 2 2 1, 3 minus 1 2 2 1. This was our signal, this was fn. Now we need to calculate f of half n. So half n, as I have told you, you just need to divide all n values with the scaling factor. So let's plot here again, we'll do it fast. So this value will be 2, this value will be 2, and this value will be 1. So n is equal to 0, n is equal to 1, n is equal to 2, and this value will be minus 1 for n is equal to minus 1, and this value will be 3 for n is equal to minus 2. Okay, n is equal to minus 1. Okay, so now what we need to do, just we need to divide by half. So half you need to divide, and okay, half and half. So this will come upside, so new signal will be formed. And the new signal, how it comes, minus at n is equal to minus 4, the value 3 will lie, and then this is minus 1 upside to minus 2. So for n is equal to minus 2, the value is -1. Okay, and for 0 to 0 it will be 0 only, so it will be 2 only. For n is equal to 2, n is equal to 2, the signal will be 2, and for n is equal to 4, the signal will be 1. N is equal to 4, signal will be 1. You can see that uh, see, for a is less than 1, signal has been expanded, that we can see that. But you can see that there are some see, whenever we'll write it down, we have to write from n is equal to -4 to n is equal to +4. Some values will be written like this value is 2, I think 3, and then for n is equal to -4, and then we'll write 0. For n is equal to -2, we'll write it as -1, and then we'll write it as 2, and then for n is equal to 1, we'll write 0, and then we'll write 2, and then we'll write 0, and then we'll write 1. You can understand it as some 0 values we are introducing. Earlier, when a was greater than 1, so there was loss of sample, and when a is less than 1, there are more samples which are 0 values. So this technique is called as zero padding. Okay, this technique is called as zero padding, and there may be some unknown values also, and these unknown values can be calculated by interpolation techniques such as Newton-Raphson-Runge-Kutta method. We can do it. So these are all some scaling property which we have seen in the discrete time signal, and time shifting property. Now last we'll see time reversal also in our discrete time signal. Time reversal, it is not a very concerned thing, because we need to just do our mirror image. Okay, so let's suppose signal is there, f of n, and the value is 4, 3, 2, 1 and 1, like this value is there, and this is n is equal to 0. And whenever you have been asked that perform f of -n, then what we need to do, we need to retain this value at n is equal to 0, and just we need to flip it. So f of -n can be written as, here 1 will be there, means this side it will go this side, and this side will go this side. So 1 will be there, and then 1 will be there, and then 2 will be there, this will come here 3, and this will come 4, and this you can write it down. Simple, nothing more than that. Just you need to keep the n is equal to 0 value, and just you need to flip. After this, if you are not comfortable in basic signals, we will also discuss this also in this lecture series only. See, there are some basic signals, elementary signals, which we have seen in continuous time signal. Let's see in discrete time signal how it does it, how we can mathematically write it. Okay, so see, one signal is there that is called as unit step signal. See, in time domain we'll write it as like this, and we write it as ut. Okay, in discrete time domain we'll write it as, see, here t is equal to 0, here for n is equal to 0, values are there. So for n is equal to 0, value will be there 1, and then for after then n is equal to 0, n is greater than 0, the values will be like this only, and it will go on. Okay, so this is called as u of n. Okay, this is called as u of n. So u of n can be mathematically written it as, un of n is written as 1, 1, 1 and so on, and the value, the arrow will be at this, n is equal to 0, the value is this. This is un, and mathematically it can be written out as like this also, 1 for n is greater than or equal to 0, and for 0 n is less than 0. This is u of n, which can be written as like this. Okay, okay, but ut, if you remember, ut can be written as 1 for t is greater than 0, and 0 for t is less than 0. If you ask what is the value at t is equal to 0, then you can do average value, 1 plus 0 by 2, 0.5, you can write it down. For u of n, if we do time shifting property, like if you perform u n plus 1, then you can understand that we need to shift it. So for n is equal to -1 also value will come, and then it will go like this. So u of n plus 1 can be written it as like this, and u of n minus 1 can also be written it as just shifted. For impulse signal, what we can do, second signal, impulse signal, and in discrete domain impulse signal, see, in time domain we can write it as like this. For t is equal to 0, and delta t is equal to 0 for t is not equal to 0, and not equal to 0 for t is equal to 0, and minus infinite to infinite delta t dt is equal to 1. This we have remembered from time domain. Now for our discrete domain, okay, what how we can write it down as, here n values is there, and the value for impulse signal will exist at n is equal to 0 only, and the value will be 1. So delta n can be written it as 1 for n is equal to 0, and for 0 n is not equal to 0. This is the mathematical representation of our impulse signal in discrete time domain. And if you want to do delta n plus 1, you can do at n, it will exist as n is equal to -1. Okay, although you can see some differentiation and integration property also in this discrete time domain, like what we were earlier doing, dt d by dt, okay, of ramp signal, you'll get unit step signal, and whenever we'll do d by dt of unit step signal, you'll get our impulse signal. This you have remembered from last lecture also. Now if you want to do in discrete time domain, what we need to do, for d by dt you can write it as r of n minus r of n minus 1 we will get as u of n, okay, and u of n minus u of n minus 1 we will get it as delta of n. You can see how, see, u of n, so you'll get from n is equal to 0, you'll get values, will get some values and so on, u of n, and you'll get u of n minus 1. If you see, you'll get from n is equal to 1, the values will start and it will go on. Now when if you can minus u of n minus u of n minus 1, you will get all the values will be subtracted, only this value will remain, and our delta n also is supposed to be exist at n is equal to 0 only. Okay, so u of n minus u of n minus 1 can be written as delta n, same as r of n minus r of n minus 1 can be also written as u of n. So the property of differentiation will exist from in discrete time domain also. So this was all about our continuous time domain signal and discrete time domain signal and real valued signal and complex valued signal. In the next lecture we will deal with some other classification of signals like even and odd signals. So for this lecture this much only. We'll meet in the next lecture. Till then, tata, bye bye, see you, have a good day.